thanks so much for the introduction. I appreciate it. So I'm a PhD student at Princeton, and I want to talk today about my latest research project, which is exploring sort of safe interactions between different programming languages in a project called Encapsulated Functions. As I said, I am also a maintainer of the Talk operating system, and while this is related, we're going to show how exactly this relates. It is a different project. This is work I've done together with my collaborators, Jacques, Tyler, May, and Amit. And without further ado, let's get right through it. So I want to start my talk with a statement which I think should not be controversial in this audience, which is that I think that memory type-safe languages are generally safer, more reliable, and more secure. They increase developer efficiency and encourage fearless development, and they prevent entire classes of bugs due to their construction. So for instance, you're going to be unlikely to be seeing use after free type confusion or other kinds of bugs in Rust. And we see that these advantages are recognized throughout industry and other circles. So for instance, Microsoft is rewriting some core Windows kernel code in Rust. Linux is obviously experimenting with Rust, as we've seen. And Google is writing some core components of their Android operating system in Rust. What we can also see is that based on their reporting, they also see a significant drop in memory safety vulnerabilities and an associated drop in the severity of these vulnerabilities, which kind of confirms that these suspicions even work, these advantages even work in more constrained environments. But this raises a question, given that in the conventional wisdom, these type memory safe languages have dynamically enforced type memory safety, which introduces significant overheads. They typically tend to be garbage collected and thus introduce unpredictable timing behavior and memory allocations, and can have quite high overhead foreign function interfaces and interactions with native code. Why do we now see this language popping up? And we attribute this to a new class of sort of safe systems programming languages that is emerging, of which, of course, Rust is one of those languages that feature a combination of compile time, type, and memory safety. For instance, reference or region-based memory management as opposed to garbage collection for more predictable memory management, and direct ABI compatibility to other languages. And they also commonly can interface with low-level assembly code directly, which allows us, for instance, in the Talk operating system to implement context switches or trap handlers in inline assembly in Rust. So a reasonable question to ask at this point is, why does my operating system still have access violations and can crash because of those? And in essence, this is kind of what we're trying to solve. But I guess a less provocative way of stating that is that parts of our systems will continue to be written in these unsafe languages, not just for the foreseeable future, but we think that's something that's effectively set in stone. This has a multitude of reasons, but partially this is because operating systems in particular are built on legacy software. They might be written for machines that are no longer commercially available, and those machines or the code for those machines might make assumptions about particular language semantics that are different between different languages. And in general, we're just getting started rewriting our code in Rust. So I guess it's just going to take a bit of time until we get there. We also have external constraints that in certain environments entirely prevent the use of safe languages. So for instance, in an embedded system, if you want to use some cryptography component, chances are that you're going to have to use go through some industrial or governmental certification processes. And those processes sometimes indirectly or directly prevent the use of certain languages. And then finally, software also provides us reusable libraries. So as we've just seen, for instance, OpenSSL is one of those libraries that's pretty universal. And while we do now have an alternative that we can use, which is very nice, chances are that you're still going to be using at least some of these libraries, even if they're written in a safe language, perhaps not the exact language that you want to use for your project. And this kind of establishes the basic premise of this work, which is that we identify there will not be a single systems programming language, and the software must continue to interact with code written in other, perhaps unsafe languages, and we need a mechanism to safely interact between different languages. And what we're proposing is in exactly such a mechanism, which is Encapsulated Functions. It's a system to facilitate safe interactions with component written in foreign languages by considering the aspects of both memory safety and type safety. Before we can go into exactly how encapsulated functions work, we first of all have to understand a bit about the particular issues we're addressing and the background. So here I've depicted a simple system that consists of memory safe application written in Rust that perhaps makes use of some cryptography implemented in C. So this could be OpenSSL, some networking library in C++, or even some math functions in Fortran. One way to realize these applications today is to use operating system process isolation, which is a very nice mechanism that gives us strong isolation guarantees between those languages, but it's also typically associated with pretty high overheads. So this means that when you want to communicate some data between your memory-safe application and your foreign library, you're going to have to incur some serialization and deserialization costs, perhaps copy some data. And even if you use efficient implementations of all of these processes, there's still going to be a context switch involved between every such interaction, which can be a pretty high cost compared to some pretty short-lived functions. Instead, what you can use is the safe language's foreign function interface, which allows it to emulate the ABI of a given other language. So in Rust's example, this could be the C ABI, and as such allows Rust to directly call functions that are written in, for instance, C. This is nice because the entire program runs in a single address space, which allows the foreign code to exchange data efficiently with the safe application. And a function call is literally the cost of a single jump. This is how something like this can look in Rust. I'm pretty sure the previous talk has shown some similar examples, and you've probably already seen something like this. We can define an extern C function symbol in Rust that just announces to the Rust compiler that there is going to be a given symbol that it is linked to, which implements a given ABI. In this particular example, I'm using this AS-encrypt function that I've invented. The particular semantics and parameters are not super important here. Just do note that it returns a Boolean value. And then in line 11, we define a Rust wrapper around this function. And this Rust wrapper then invokes this function on line 13 and stores the result in a variable, and finally moves this variable into an enum, which is defined on line 6. So pub enum message is an enum which has an encrypted and unencrypted variant. Notably, because this is a tagged union, both of these variants are going to be stored in the same memory location and are thus overlapping. Given this example, one of the most apparent ways in which this can break Rust's memory safety, as we've heard in the last talk, is when, for instance, the foreign code is not well behaved. So Rust may have some allocations that it assumes exclusive ownership over, and so when foreign code is either handed a reference which it shouldn't write to, for instance, it's a shared reference in Rust, or just invents some other arbitrary pointer, it may endanger Rust safety in a variety of ways simply by writing to its memory. And so memory safety bugs in these libraries compromise the overall system safety. There is, however, also another type of issue, which is a bit harder to spot. Even if we assume that these libraries are entirely well behaved and our interface code with them is sort of superficially correct, the different cross-language semantics between these languages can introduce additional hazards. And to explain this issue, we're going to have to go into a bit more details of the previous example, particularly this pub enum message type. So we can see here again that this enum type has two variants, which I've outlined here on the slide, and I'm depicting their memory layout. So we can see that the first word of memory is occupied by an enum discriminant, which just indicates what the active variant of that enum is right now. And then all of these subsequent data fields are just laid out in memory effectively, according to their alignment right after this discriminant value. So we can see here that the message encrypted variant has a discriminant of 0, and the message unencrypted variant has a discriminant of 1. This is, however, a rather inefficient representation, and Rust recognizes this. In particular, bool is defined sort of semantically equivalent in Rust to this enum that I've depicted here. In particular, it's sort of a 1-bit value that can either assume the variant false or the variant true. And it is, however, stored in a memory location that occupies at least a full byte full byte's worth of memory. And so what this means is that we have a couple of other uninhabited values that we could be storing in this memory location where the bool is stored. And so Rust performs an optimization that is known as niche filling, where it actually combines those first two fields, the discriminant and the Boolean value, and treats both the values 0 and 1, so all valid values for a type of Boolean in this first field, and then uses the first uninhabited value of that type to denote any other discriminants that we might wanna encode. And so ultimately this saves us a whole lot of memory, and that's a nice optimization. This can break, however, when, for instance, Rust then reads a value of type Boolean that it assumes of type Boolean that has been modified, for instance, by some foreign code. This is because foreign code does not necessarily need to adhere to the constraints that Rust places on its types. And so if, for instance, Rust were to read a numeric value of 2 in this Boolean field, then we could be storing this message encrypted variant here and storing a vec besides the Boolean as illustrated in the enums definition. But we could be reading back because we're storing this value 2 in here, and Rust assumes that the Boolean type is valid, and so it doesn't perform any other checks, the unencrypted variant. In this particular case, we would be able to safely dereference what we believe to be a C-string type, but is actually a vec pointer, and that ultimately leads to undefined behavior and, in practice, segmentation fault. And so Encapsulated Functions is a project that tries to address both of these issues through a set of interworking mechanisms. We introduce a mechanism called safe trampolining that allows us to isolate the memory between safe and untrusted foreign code. This mechanism is platform agnostic and retains sort of general function called semantics. Function calls remain to be synchronous, and so it's more or less a drop-in solution for existing bindings. And then we combine this with a type infrastructure that is responsible for securing these cross-language interactions in these more tricky cases where we have sort of mismatches in the definitions of types across languages. And this is enforced entirely at compile time, so you should be unable to write any code that violates these constraints. And if it doesn't, or when it does incur runtime overheads, those should be minimal. We'll be focusing on the safe trampolining aspect first. It's worth mentioning at this point that Encapsulated Functions does rely on the presence of some memory protection mechanism in the system. So we're agnostic over the exact mechanism used. This could be a hardware-mediated memory protection mechanism provided by the operating system, for instance, regular address space isolation, as is implemented in the memory management units of the computers we use today, or more primitive mechanisms such as memory protection units, and more modern mechanisms like x86 memory protection keys, which is a mechanism that we're using to evaluate encapsulated functions on. We could also be compatible with something like software fault isolation that does not rely on the presence of hardware mechanisms. However, we do not explore that at this point. And so this is depicting a regular sort of Rust application, in this particular case running in the context of a microcontroller system. So we have a memory map that contains a couple segments, in this case some RAM, some flash, and some memory mapped I/O. And when we now load a library into this system, we load it into a set of coarse-grained allocations that is disjoint from any Rust allocations. And so here we're loading a library with its RAM contents and flash contents placed in the appropriate memory allocations. And we might even give it access to some hardware peripherals. This could be useful, for instance, for a cryptography accelerator. We then set up a memory protection mechanism to allow our foreign code only access to these particular allocations. It must be unable to access any Rust allocations, or at least write to those allocations. The converse is not true for our Rust code, however. Because we assume Rust to be well-behaved and a type of memory-safe language, it is going to be limited to dereferencing its particular sort of currently valid allocations. And as such, we can and indeed must allow Rust to access or to be able to access this foreign memory. When we implement this in practice, there's kind of three key challenges that we need to solve. We need to load foreign libraries into a disjoint set of allocations first. We then need to set up memory protection, set up the memory protection mechanism to enforce sort of the protection policy that I've illustrated on the previous slide. And then finally, we need to switch protection domains. And these are arguably the most interesting of those challenges, and so we're going to be focusing on that. So the problem is basically that we must restrict untrusted foreign code to its own memory allocations. And the intuition behind this is quite simple. We can just enable memory protection, execute the foreign function, and disable it again. However, when we do this naively in practice, there's a couple of challenges that we need to solve. For instance, we cannot simply enable memory protection in the host language itself, in our case in Rust, because we don't have fine-grained control over the sort of end result, the binary that the Rust compiler produces. Between any two statements, Rust is free to insert arbitrary memory reads and writes to allocations that it deems valid. And so once we enable memory protection and are still in the Rust context and want to call another function, this may actually break our host program ourselves because we could get access fault violations. For obvious reasons, we also can't rely on the foreign code to enable this protection mechanism because it's untrusted by definition. Instead, we need to switch exactly on the function call itself, and that's rather tricky. We also need to maintain access to function parameters and return values when we execute foreign functions. Depending on your architecture and depending on the precise callee, so the function signature that you're calling, some arguments might be passed in registers, whereas other arguments are passed on the stack. And if we simply call a function from within Rust, Rust is then going to spill those arguments on its own stack, and that is going to be located in a memory region that is inaccessible to our foreign code. And we solve these challenges through a callee-specific safe trampoline that I'm going to be illustrating next. So this trampoline works as follows. For any given C function definition, in this case, I'm taking one which is called random bytes buff that takes a pointer and an integer and returns another integer. We then, using Rust bindgen, first of all, generate a Rust function signature that implements this function's ABI and calling convention. So we denote it here as extern C to instruct the Rust compiler to, when this function is called, prepare an execution environment that is effectively appropriate for calling this function. It has all the right arguments loaded into registers and spilled on the stack. But obviously, we don't want to just invoke this foreign function in this execution context, because then we would be invoking it with Rust's privilege set. Instead, we're going to be aliasing this function to a custom invoke symbol that we're introducing here, which is implementing our trampoline mechanism to, in sort of one atomic step, enable memory protection and switch to foreign code. So this is written in assembly typically, and its basic job is effectively to just copy all the stacked arguments, enable memory protection, invoke the foreign function, and then when it returns, which works through a springboard mechanism that is dependent on the precise memory protection mechanism that you're using, we then disable memory protection and copy the return values back, in addition to any sort of required status flags. So for instance, if the foreign code were to have an access fault violation, we would want to return to Rust and actually indicate that there has been an error. However, this is still not quite sufficient because we might be loading multiple instances of this library into our program. And so this invoke trampoline can't really know which library instance it's currently talking about. It needs to know, for instance, where the foreign memory is located, where the current stack pointer is to copy those arguments. And as such, we're adding an argument, we're appending an argument to this function signature, which we call context. Here we rely on the fact that when you append an argument to a function signature in all of the calling conventions that we're aware of, this does not change the location of any preceding argument. So this is effectively still a compatible execution environment. Another problem is that now we have this context struct, and we can resolve a couple of things about our library, but we don't know exactly where this argument is going to be passed in the function. And so instead of just providing one such invoke function, we make this into a generic function that is generic over the amount of bytes spilled on the stack by that particular function signature and the location where this context argument is being called or is being passed. And so in this particular example, the context argument is passed in the second argument register of, I think this was a RISC-V based calling convention, or the RISC-V-C calling convention. And now, and we do this, we generate these arguments by extending Rust bindgen with a static analysis pass to analyze our function signature and sort of have a small implementation of the particular calling convention for that architecture. But that's quite brittle, so in the future we would actually like to query the LLVM backend. That's still to be implemented. And then finally, because this function is now a different function signature and you need to pass this additional context argument, and also we need to do some other work such as interpreting whether the function actually had a fault violation and returning an error result instead, we provide a wrapper function signature that then simply calls this function. So with this mechanism, we now can transition from Rust code into C code, which is quite nice. But this is not really particularly useful in isolation because of the problem that we talked about where Rust technically is able to access foreign memory based on the memory protection policy, but it can't do so because it's limited to only accessing its valid allocations. Rust does provide the unsafe escape hash for us, which is nice. It allows us to upgrade arbitrary pointers to references, but as the name implies, that's also really dangerous if you were to violate any single one of Rust's guarantees that it requires you to maintain. And so what we instead propose is another component, which is the type infrastructure that is responsible for securing these cross-language interactions. We base this type signature on simply a raw pointer type. We treat this as an arbitrary pointer into foreign memory, but really it can point anywhere. It can point to a dangling value, misaligned value, value of an improper type. And because it's not safely dereferenceable, retaining this value and passing it between safe and foreign and safe Rust code is going to be sound. Then from this value, we can perform an operation which we call upgrading. Upgrading takes this value and checks a couple properties, namely whether it's well-aligned and a mutably accessible object, and whether it's entirely contained within those foreign memory allocations, which ensures that it's disjoint from any Rust allocations. And then using this EF_mut_ref type that we're creating here, we can support a safe write operation, which is unable to violate any of Rust's semantic guarantees. Then finally, from this type onward, we can also run a function called validate that then actually checks whether the pointee of this reference happens to be an object that conforms to Rust's requirements on valid values. For instance, whether a Boolean is only going to contain a value of 0 or 1, not 2. There are some objects for which we can check this at runtime, namely Boolean, char, or string. There's other objects or other types like references for which we simply cannot check this, and thus this operation must be impossible. And then there's yet another couple others like integer types, which are simply universally valid. They don't have any particular constraints imposed on them. We can also represent this on sort of a timeline where we take this raw pointer and then we upgrade it into this EF_mut_ref, which continues to exist for entire program execution, and then validate it into this EF_val, which also continues to exist. However, while that's safe in isolation, it can actually be quite dangerous when we pair it with some other operations that encapsulated functions exposes. For instance, let's assume that you have a pointer to a Boolean and you upgrade it and you validate it, and so we're all good. We can dereference it into a proper Boolean type. But now we invoke foreign code, and because it has access to all of its memory, it can simply retain the original pointer to this value and write an invalid value according to Rust's definition to that memory location. And so invoke is kind of a dangerous operation where beyond the point of invoke, we cannot rely on these guarantees to be valid any longer. Quite a similar issue exists for the mutable references, where if we free the memory that belongs to the underlying allocation, accessing this in the best case is just going to result in an access violation, and in the worst case, Rust may actually reuse this memory for some proper Rust allocations. And now our EF_mut_ref type has successfully produced mutable aliasing, which is unsound and we thus must prevent. We fix both these issues by introducing two new types, which we call access and allocation scopes. Those function quite similar to capabilities or Margaret types, if you're familiar. The important invariant that we need to maintain on those types is those are singleton types. There must only ever be one instance of each of those per foreign library that we load. And when we now have such a type, we can extend these operations that we have here to make use, to sort of use them to bridge Rust's concepts of borrowing and lifetimes onto foreign memory that is otherwise not conforming to those requirements. We start by taking this validate function and having it take a shared reference to this access scope. Thus, it sort of adopts this access lifetime here. And while that's in isolation is not particularly useful, we can take any number of references, any number of shared references to a type. When we pair this with a modification of the invoke function, namely having this take a unique reference of this capability, the Rust compiler will then ensure that beyond the point of invoking this function, no validated references that borrow the previously active shared lifetime or sort of shared reference lifetime of the access scope will be in scope anymore, and thus no validated references sort of can still be dereferenced across this point of invoking a function. We do a quite similar modification using allocation scopes to the upgrade operation in free. Namely, we take a shared reference to our allocation scope in the upgrade operation, which binds the immutable reference and transitively also the validated reference to an allocation scope. And then we take a unique reference in a call to free, which then ensures that beyond that call to free, these validated reference or these upgraded references must have gone out of scope. In practice, our implementation does something a tiny bit more complex. Namely, not every single reference is dangerous to keep around in the presence of any given single free operation. There are free operations which simply do not deallocate any memory belonging to particular references. And sometimes we can actually steadily determine this in our code. And by extending the immutable reference type with an additional lifetime, we can, for a subset of these references, prevent them from going out of scope across certain free functions or free invocations. And so with this system in place, we can now safely dereference values in our foreign memory from within Rust, subject to a couple of other restrictions, such as the foreign library not being multi-threaded. What remains to be seen is actually the sort of what overheads this mechanism imposes. And for this, we perform some evaluations using our implementation, which is a research prototype. So it's not quite ready for prime time yet. In particular, the code quality still needs to be worked on a bit. We have two implementations, namely one for the Linux userland using an Intel MPK or x86 MPK mechanism. Memory protection keys is a quite attractive mechanism for encapsulated functions because it is a hardware-based memory protection that you can control entirely from within user space, and thus you don't incur a context switch across the protection domain switch between different language components. We also have an implementation for the TOC operating system kernel on the OpenTitan Silicon Root of Trust, which is a RISC-V chip running at 24 megahertz using the physical memory protection mechanism of RISC-V. And we extend Rust bindgen to generate these encapsulated functions bindings from C header files. We evaluate sort of three representative workloads, which are libsodium as a popular high-level encryption library, broadly as a compression library that's used by Google and Dropbox, and cryptolib, which is a hardware-accelerated and hardware cryptography library for the OpenTitan Silicon Root of Trust. And what our evaluation shows is that in most cases, the overheads that encapsulated functions imposes are quite negligible. So we compare ourselves against an unsafe baseline that neither performs any memory protection nor performs any validation operations. So the validation operations here indicate that we only use our type infrastructure and impose that on the code. The invoke-only benchmark only uses the memory protection but does not perform any validations. And then encapsulated functions is sort of those two combined. It should be noted that in the first two benchmarks, we do actually perform some validation in practice. So the fact that these overheads are quite minimal is just an artifact of the Rust optimizations on these benchmarks and them being quite lightweight. So here we perform the validation that the strings returned after these functions are actually valid UTF-8, which Rust requires us to maintain. For the hash function, we also invoke our validation routines, but because the hash functions output an array of integers, of bytes, and those are universally valid, the Rust compiler is actually able to optimize these calls away entirely. We have a slightly more pronounced overhead on our second target, which is the OpenTitan FPGA implementation running at 24 megahertz. So obviously these numbers are quite a bit larger on an absolute scale. Relatively speaking, we're imposing sort of a 50 millisecond overhead compared to the unsafe baseline. And this can be explained by two factors. First of all, the PMP, physical memory protection, requires us to do quite a bit more operations to actually perform a perfection switch. Effectively, we're performing a context switch in this case. And the other reason is that because we're running an HMAC workload, we do actually need to copy quite a bit of data into the unsafe foreign code domain for the HMAC to be able to operate on that data. And so about roughly like 80% of the overhead imposed here is actually spent on copying data versus switching the protection domains. And so to summarize, encapsulated function secures interactions with foreign languages through its combination of both a safe trampoline mechanism to isolate the memory of foreign and Rust code, and by securing these cross-language interactions, with our set of type abstractions. The preliminary results that we've seen are pretty promising, and we would like to extend our work by improving the calling convention analysis that we're doing. Right now it's a bit brittle, so if we use the compiler backend, hopefully that should be much more stable. We want to do a thorough safety and soundness analysis of our code, because obviously we internally use quite a bit of unsafe Rust, and so we would need to be careful that we're not actually violating any of Rust guarantees. We're pretty confident in the overall sort of setting of this. And in particular for Linux user space, we have experienced that some libraries, such as we have a benchmark which is using OpenGL, that doesn't quite work with this because they rely on global symbols and shared state too much. And so if we were to sort of rework the dynamic loading and the way that we use the dynamic loader in our implementation, we might be able to support even more targets seamlessly. And with that, I would like to thank you very much, and I'm happy to take any questions.
Excellent. Well, who dares? There are 2 hands there. How would this work for dynamic linking?
That's a good question. So we are in fact only supporting dynamic loading right now. So the way that we achieve this separation of different sort of disjoint isolated coarse-grained regions is we use a function called DLM open provided to us by glibc that loads where we can effectively load libraries into their own namespace. And so I think, does that answer your question? That effectively means that we can sort of dynamically load libraries.
Yeah, it does. Thank you. Thanks. That was interesting and a lot to take in. I have something that I didn't quite understand, which is when I pass a data structure to C, for instance, do I actually copy it, or can I pass a reference? And if I'm copying everything, isn't that expensive? And do your benchmarks show that? And then a related question is, I didn't understand the multi-threading story.
Yeah, that's a good point. So there's sort of 2 models of this solution. Technically, it doesn't violate Rust safety, or Rust soundness at least, if you can read Rust memory from within a foreign language. And so depending on your particular thread model, you might enable read access to all of Rust memory, in which case you can skip copying in the majority of cases. In our evaluations that we do, we did copy data. So all of these are copying admittedly rather small payloads, so on the order of a couple of kilobytes, because these functions themselves already were quite long running compared to the overhead of copying. And if we had copied more data, that would have made those functions take longer and would have effectively eliminated even this tiny bump that we're seeing in the overheads here. So copying does incur overheads if you do enable read and write isolation of memory. So that is quite expensive compared to, of course, not copying. For the second question, that was about the multi-threading story. So the reason why we don't support multi-threading right now is that our type infrastructure kind of relies on the temporal invariance that we're maintaining here with respect to these capabilities. If our foreign code were to be able to execute while we are assuming to have unique ownership of this value, and while we're assuming that it doesn't change, then we can no longer rely on these guarantees. So we're still kind of figuring out the multi-threading story here. What you can do is you can use multiple instances of a library across different threads, and you can have your Rust part be multi-threaded. Just the foreign function needs to be single-threaded.
There's another hand.
And great thought, thanks.
Thanks.
I was wondering, does this system support like callbacks? Like some applications expect a function, like I think OpenSSL is one, for instance.
So we have a proof of concept implementation of this, and it seems to work quite well. It fits actually quite naturally. It's certainly less polished than all the other consistent components we have. So before I commit to us supporting callbacks, that's like the small asterisk, but there's nothing really preventing this from happening. The one thing that you need to be careful about is what we've also seen in the previous talk, is that you need to catch unwinds and panics in a callback when you call Rust, C from Rust, Rust from C from Rust, yeah.
Got it, thanks.
There's some hands at this side.
Does this work with multiple libraries like recursively?
So you would say that we are effectively this is loading a library in the library that we're then interacting with?
Yeah, so if you have a C library that uses a C++ library, which you then call from Rust.
So as long as the C library dynamically links to that other library, or statically for that matter, this should work because we're then loading both of those into the same linked namespace and isolating both of them. In fact, all of these benchmarks that we have for Linux user space do use something like glibc, which works. But if those libraries were to then use dlopen and sort of dynamically load other libraries at runtime, that is currently unsupported. That's kind of an implementation detail in our current version.
All right, thank you.
Hi. So newer Cortex-M microcontroller chips usually come with trust zone nowadays, which has some overlap with what you're saying or what you're talking about here. I was wondering what your opinions are, because it doesn't look like you're using it. Maybe there's good reasons.
So I will admit that I have limited understanding of Trust Zone M. That's the microcontroller variant of Trust Zone. As far as I'm aware, it's effectively an additional layer of memory isolation that has some stronger guarantees with respect to control flow. In that case, I don't think there would be anything preventing us from using this. In fact, we do have a prototype which uses the ARM Cortex-M MPU. So that's the memory protection mechanism that is effectively, the equivalent of a RISC-V Physical Memory Protection on ARM. We aren't currently using Trust Zone M.
Okay, thanks.
There was a question there at the back.
Does this require some special annotations in order to call the functions?
Yeah, so it doesn't really require some special annotations. Instead, you use a slightly different function signature. So here's actually a small example of how this can look like. So we have this run function. We have a bunch of convoluted type parameters that we require here. But when you then actually want to call a function, so this is an example that I prepared, was called evil bool writer, that actually tries to write to a reference owned by Rust. Then you can just use our lib.dot signature here, and the remaining function arguments are effectively identical, except for that we are identical to what a regular FFI binding would expect, except that we also pass an additional access parameter here. Yeah. So if we run this right now, hopefully this actually is segmentation fault, because this is not supposed to work. If we hadn't used encapsulated functions, this would have worked silently. And instead, if we then actually allocate memory in the foreign functions region, we can then safely write to that memory. But then we realize that this function writes a numeric value 2 to that boolean, and when we then try to use this value, it's impossible to use this reference without actually validating it. And when we then do a call to validate, which is done here, we can see that it panics with the message invalid bool because that validation has failed.
Any more questions? There's a hand there. On the right side of the... Yep.
In the presentation, you mentioned using niches and how like C code could affect how Rust treats a tag enum.
Right.
I don't understand how the validation could check that the enum tag got changed. Could you explain a bit more?
Sure, yeah. So the way this works is we don't check it on the enum tag itself. We check it on the value being retrieved from foreign memory and then copy it into Rust memory, where we would then insert it into an enum. So in fact, this example is actually is not only just contrived, but this actually doesn't really work on modern Rust, because Rust does actually happen to, for any enum that has a sort of like a 1-bit representation, it inserts an additional AND instruction that we cannot otherwise explain other than this issue being so prevalent that Rust actually protects against the naive case of a two-variant enum being communicated to C. So in fact, we reproduce this issue and actually get a segmentation fault when we extended this to a third variant and not use a bool, but our own custom bool type. But what we do is we do it on retrieving this value. And then once Rust retrieves that value, for instance, our 3-variant pseudo bool, it assumes that value to be a valid instance of its type. It doesn't perform any additional checks. And actually, in fact, it moves it directly into the storage location of the discriminant of that resulting outer enum. And so it doesn't perform any checks at all. And we perform that check on loading the Boolean into Rust.
That makes sense. Thank you. Is there a last question? No hands? There's one hand.
What if I'm a Rust library and I expose a C FFI and I have a C program that's calling into me? Can I use this mechanism in order to protect my objects from the application somehow corrupting the memory?
So that's quite an interesting question. We haven't looked at this before. There's some related academic work on that particular threat model, but those I don't think that those actually explore the type infrastructure parts of this. So they're only concerned about memory safety. There is some related work that I could point you to offline, but they don't consider the type aspect. And while I guess there would be a way for us to port our contributions to those implementations, we haven't really looked into that at this point.
All right. Let's thank Leon again for this great talk. Thanks.